In this lesson, we're going to learn what a disparity map is and how it's usually generated. So I've just opened up a new script here, and inside of our project files, we have a sample disparity EXR. So let's drag this into our project and take a look. Now, inside of this file, we have a disparity channel. However, if we look at the channel dropdown, it looks like we have nothing. And that's because we need to set up our multiple views. So in the node graph, let's hit the S key, and let's change our format to the size of this image. And in the views, let's set up our views for stereo. And now, if we go back to our drop-down here, we can see our disparity. So let's take a look at the disparity map. And we get this pretty extreme image right here. Now, if you look at the bottom here, you'll notice the value range that this map is going to. So over here in one of the corners, we get up to about 20. And then as we get closer to the camera, we get into the negative values. So negative 30, negative 35. So what these values actually correspond to is the difference in pixel positioning for every feature in our image. So to view this, let's actually come in here and grab something. So let's go back to our RGB, and let's take a look at this mole here. So right now we're in the left side, or we're in the left view. If we switch to the right view, we can see this mole is shifting over a few pixels. Now, if we know exactly where this pixel here will shift to, then we can do a lot of interesting things behind the scenes. So let's take a look here. So I'm going to hold the control key, and we can see that this is about X is 201. If I jump to my right view, for that same approximate image, it's X 206. So for our left view in this area here, we should have a value of 5 because it's a 5 pixel shift from the left image to the right image. So let's go back to our disparity channel here, and let's take a look. And so we can see down here our red channel is at 4.61, or about 5. And so our disparity has essentially two parts to it. The first is the left side to the right side, and the second is the right to the left. So if we go to our disparity channels here, you'll notice that we have a disparity L and a disparity R. So the disparity LX is simply saying in this channel we have the X position or X offset of how to transform a pixel from the left image to the right. So inside of this pixel right here, this ultra pink pixel, we're essentially telling Nuke that to move this pixel into the right view, you need to move it right 4 pixels. And then it would be right about here. And if we jump to our right, we can see that that is correct. So we obviously are using a 3D scene here. So the next question you might ask yourself is, can this technique be used with live footage? And the answer is, it really can't. For live footage, you're going to need the Foundry's plugin Ocula to actually create the disparity map, because we're simply using 3D depth information and converting that into a disparity map. So the techniques taught in this course will not work to generate a disparity map for a live shoot. However, if you have 3D depth pass, so we can jump to our depth channel, if you have any kind of 3D depth information, we can use this information to actually generate a disparity map. So we have to make sure that we have left and right depth information, and from this we can create this disparity channel. So that's all well and good, but the question really is, why do we need this disparity channel? Well, it's actually an integral part to many of Nuke's stereo tools. So let's add in a new node beneath our current disparity. So first, let's drop in an anaglyph node, and that just lets us see the separation. So let's say we want to change this image so that the scientist is on the screen. And that would mean we need to shift either the left or right image, left or right, to make sure that it has none of this red and blue offset. We can do that with the stereo reconverge node. Now, in an earlier lesson, we learned how to use this convergent offset to manually place it. So if we want the scientist's head to be on screen, we would need to do a convergent offset of about this number. Now, this is, of course, a manual process, and we have to do it by eye. it would be really nice if we could do this automatically, and we can. So let's delete this convergent offset value here, and let's actually type in 0, and we now have a convergence point, which is actually reading the data out of our disparity map to come in and move our images around. So if we want the scientist's head to be at a 0 level convergence, or in other words, to be on the screen, we just move the converge point to that location. Of course, if we want to move it to the back, we can move that to the background, and now everything will be popping out of the screen. And if we want everything to be popping into the screen, we can set the converge point closer to this cup here, and then everything will be seen as if it is past the screen or inside of our actual monitor. So this is an extremely powerful tool of how we can use this now to reconverge our image dynamically based on a position. And so now, as we'll see later on, we could connect this up to a tracker and keep a single point in our image always being converged. Now this is extremely powerful, but it is not all we can do with a disparity map. We can also copy things from one image to the other. So let's say we drop in something simple like a sparkles. Now the sparkles is created, and let me actually pull the position down here, inside of our image. Now by default, these sparkles don't have any positioning in 3D. So let me just size this down so it's a little bit easier to see. And let's say we want these sparkles to be in the corner along the back wall. Well, right now, if we put on our 3D glasses, we can see that these sparkles are actually placed. Now this comes about from our disparity map. And so if we scroll down on our sparkles here, we have a position tab. And using this, we can actually correlate the right and left position using our disparity map. So if we click correlate right from left, what we're doing is we're saying, take a look at our disparity map and then offset this to place it into 3D space. So after correlating that, and if we put our 3D glasses back on, we can see now that our sparkles effect has been pushed back very far in the depth. That's because our correlate function here was looking at the position of our sparkles effect here. Let me turn my offset or my overlay back on, and then it was grabbing the data from our disparity map to offset the view in the other eye. So if we take a look at this, you can now see that our sparkle is placed correctly in both views. So as you can see, there's really a lot of things we can do with the disparity map inside of Nuke. And we're really only going to touch on the basics. There's quite a few different nodes, and there's a lot of potential for this disparity map system. And what you probably don't know is that you can use your 3D depth passes as a disparity map with a little bit of editing. So you probably already have access to this information in its raw state. So in the next lesson, we'll learn a little bit more about how we're going to convert our 3D depth pass, which again is just a simple depth pass, into a disparity map by offsetting for our 0 parallax point.